So here we have a multi-step synthesis problem, and we have a chemist that starts with an alkyne and does a bunch of reactions, and you get a product. And the question is asking you to identify what is the structure of A, B and C are, and they're asking you the names of these molecules. Okay, so so you start with an alkyne, right, and you treat it with sodamide, Na, NH2 and ammonia. So sodamide is used in conjunction with ammonia because ammonia is the medium, which is a solvent, and sodamide is the strong base. And when sodamide is protonated by the alkyne, right, then you have the acetylide. Okay, and the proton that is picked up by the sodamide is going to become ammonia as well. So you have sodium acetylide as the first species. Now when you treat this with C5H11Br, you have a bromine, a leaving group in the molecule, and this acetylide can act as a nucleophile, and you will end up getting a substitution on the alkyne part. So you're going to have C5H11, and what happens to the Br? Br goes with sodium and you get sodium bromide. Okay, so what exactly the C5H11 is, we don't know yet, but we can make that out from the structure of the product. Okay, so that's that. Now we have Lindlar catalyst. Lindlar catalyst is nothing but poisoned palladium catalyst. So if you have simply palladium and hydrogen, you are going to convert this into an alkane. Okay, if you don't have anything else other than palladium and hydrogen, you are going to convert your alkyne to an alkene and further to an alkane. But since you have Lindlar catalyst, which is a combination of palladium, hydrogen and quinoline and barium sulfate, right? So quinoline is a naphthalene looking molecule, except it has a nitrogen in one of the positions. So that is going to be your Lindlar catalyst, and Lindlar catalyst reduces an alkyne to an alkene, but it doesn't reduce it any further, okay, because it is poisoned. So that's what happens, and that is a structure of C. And now when you treat C with HBr, you're going to have a polar addition. The proton will make a bond with the terminal carbon, so you'll get a carbocation on that secondary carbon, and the bromide will act as a nucleophile to the secondary carbocation, and you'll end up getting the Markovnikov product. So C5H11, and that is your bromine. So if you look at the product structure, that C5H11 is going to be a branched structure. So you have, that is the actual structure. So 1, 2, 3, 4, 5, 6 and this is going to be 5, 6, excuse me. Okay, so there is a carbon there. So if you look at the alkene, therefore the alkene also is going to have the same structure, except you will have a double bond over there. So that is the alkene structure. And when you name an alkene, you have to make this carbon 1 and 2, and same thing for an alkyne. Alkyne that you have here is, and for the alkyne 1, 2, 3, 4, 5, on the fifth carbon you have your branching. So 1, 2, 3, 4, 5, 6, that is the structure of your alkyne. So the first answer we already discussed, it's the acetylide anion. In synthesis 1, compound B is this alkyne, and this is a hexyne. Okay, so these options are wrong here, which is why I didn't really mark it. I forgot that I did not mark it, and I kind of got confused a little bit there. So this is your hexyne. These options are wrong. Alright, so this is a hexyne, and it is a 1-hexyne. And since you have methyl on the 6th position, this is going to be a 5-methyl. Okay, 5th position, 5-methyl, 1-hexyne. Okay, so 5-methyl, 1-hexyne. So all these options are wrong. Okay, so now let us look at the second question, or the third question here, right? The compound structure C is again same as the naming for an alkyne. The alkene has to get the lowest number in an hydrocarbon. Therefore this is going to be 5-methyl 1-hexene. So 5-methyl 1-hexene, or it could also be called as hex-1-ene. Okay, all of these options are so both these naming is correct. So 5-methyl 1-hexene. Okay, so it also let us take a look at the second one. So in synthesis 2, compound D is what? Okay, so you have bromine, electrophilic aromatic substitution reaction. So you have benzene, you have bromine, right? And if you add FeBr3, what happens is, just like you see for aluminum, FeBr3 acts as a Lewis acid. You get that species. Ion gets a negative charge here, right, formal charge, and you get bromine, and now the bromine here is highly activated, and therefore it will be able to react with the benzene ring, and so the lone pairs attack that, and this bond is going to be broken. So you end up getting FeBr4 negative charge, and you get bromine positive charge, double bond. Okay, now what happens is, benzene now does not have aromaticity, so it is going to take away the hydrogen's electrons to make a bond, and you will have a substitution reaction, which is not an SN1 or SN2. This is what you call an addition elimination reaction. So you add a group and you eliminate another group, and that's essentially substitution. So that's how electrophilic aromatic substitution reactions work. So we have our bromobenzene. So that is the structure of product D, which is just bromobenzene. Okay, and now when you treat your bromine with an alkene, the presence of an acid, okay, you will have a second electrophilic aromatic substitution, because here the electrophile is going to be your ethylene carbocation. As I just mentioned yesterday, this is not the exact carbocation that forms, but it is something that is useful in understanding how this reaction works. So there is not the exact carbocation to write, but that being said, we can still use this kind of carbocation to understand how the chemistry works. So you will have a second electrophilic addition of the benzene ring, and since bromine has a lone pair, right, it can donate electrons into the ring, and therefore it is going to be an ortho para director. Okay, so now if I want to show a para direction, right, I can write that kind of electron pushing, and you can see the electron gets on to the para position, and if you just draw an arrow like that, right, you can show that you have a resonance form where the electrons are going to be in the ortho position. So bromine is ortho and para directing. Okay, so you can either have an ortho substituted product or a para substituted product. Both of these will form. Okay, so bromine is ortho para director. Keep that in mind, because it has a lone pair. It is a mild deactivator, so it's ortho para directing, but it is also deactivating, which means the reaction is going to be slower than benzene, but it is going to have an ortho para direction. So halogens are the examples. Most of the other ortho para directors are going to also be activators, which makes the ring react faster. Okay, hopefully you guys understand what I'm talking about. Okay, so these two are the products you will get. So that is what structure E is going to be. Now if you treat E with KMnO4, especially in acidic condition, usually this is performed in acidic condition, or it could also be sodium dichromate oxidation. Both KMnO4 and sodium dichromate will give the same outcome, which is converting the alkyl chain on the side to a carboxylic acid. Okay. okay, carboxylic acid. Now one thing that you want to avoid is because you see only one carbon in the product structure here, if you're just looking at this without looking at this whole, like, ethylene added to the benzene ring, you will think that you have a methyl group. Because you see only one carbon here, you might be tempted to think that the precursor, right, also has only one carbon, which is not true. Okay, so the thing with alkyl benzenes is, even if you have a chain that is, say, 5 carbons length, right, 1 2 3 4 5, and in fact even if you have branching, as long as you have at least one hydrogen on that benzylic position, okay, phenyl ring, benzylic, very similar to an allylic, right, phenyl ring, that carbon is called a benzylic carbon. As long as you have at least one hydrogen, if you subject it to KMnO4 or sodium dichromate, right, in sulfuric acid, these are both very strong oxidizing agents, right. When you subject KMnO4 oxidation or sodium dichromate oxidation on a benzylic carbon containing molecule, when it's an alkyl chain, all the carbons will be consumed and you will be left with only one carbon stuck, which is going to be a carboxylic acid. Okay, so therefore for that question the answer is going to be para-ethyl bromobenzene. Okay, para-ethyl bromobenzene. But as I also mentioned, right, you will get both ortho and para. There is no doubt about that. But para is going to be the major product between these two, because ortho is slightly sterically hindered because of presence of any group. It could be bromine, because it's a large group, there is a bigger steric hindrance. Whatever you have, para is going to be the major product between ortho and para, because the ortho position is sterically hindered. But that being said, ortho and para are going to be formed predominantly with ortho being, para being the large product, ortho being the second major product, and meta is formed in really small amounts. Okay.